Hello students, the next topic we are going to discuss is about radial basis function network. So RBFN. So in this type of network, we will include the function approximation, classification and regression. So previously we have done with the classification, but we don't have the approximation and regression. So in this particular network, we can incorporate all these features. So this will consist of three layers: input layer, hidden layer, and output layer. So coming to the input layer, as we have seen, it consists of all the input node and whatever the data received from that particular node. Hidden layer will have the radial basis functions, basically Gaussian functions as activation function. And the output layer will have the linear combination of output of all the hidden layers. And what is a working principle? So in the radial basis function, each hidden neuron computes the distance between an input and a center vector. And output of the each neuron is determined by applying a radial basis function with the distance. So what it will do is it will compute the distance between what is the input and center vector of the complete that particular network. Then it will calculate the output with the Euclidean distance with the help of the radial basis function. And what are the weight and bias? The output of the radial bias will be linearly combined with the weights using weights like bias term and to produce the final output. Okay. So only thing we have to remember in this particular working principle is it is going to calculate the distance between input and a center vector of the given input. So the key feature is you'll have the localized response. It will provide the response. Hidden neurons respond strongly only to the inputs near to the center. See, as we are only concentrating on the center vector, it will respond to the center vector immediately when compared to the vectors which are far away from that particular center. And training involves parameters of the radial basis functions, like what is their center and what is their width and weights of the output layer. So always it will train in such a way that it will respond to the center of the vector which is available for each. And it will these applications can be used for time series prediction, control systems, and for complex functions. So if you see this image processing, pattern recognition, why? Because in the image also you'll have the pixel position. Accordingly, you can use this radial basis function networks for that. And what are the advantages? These are very fast in training. These are flexible and interpretability will be more. Okay, so it will be trained easily. Like for multi-layer perceptrons, it can have the continuous function and hidden neurons, and it will interpret more when compared to other models. So disadvantages, it will become very complex as the number of training samples increase because as the number of samples increase, it will become very difficult to calculate the distance between the vector, input vector and the center vector. And overfitting, if data is not properly regularized or if you are not able to create or calculate the center point, then it will be difficult for calculation. So the mathematical representation, so this can be expressed as y of x equal to 1 to n wi of phi of x minus ci plus b. So this is the formula where phi is the radial basis function, so which we have to define. This is the phi of r, this is a radial basis function. This is a Euclidean distance. We know the Euclidean distance formula. Wi are the weights, so these are all the weights, and b is the bias term. So the basic representation, mathematical representation. So we are taking with one example that is sine of x. So here I have x equal to 0 to 6 and y is the sine of x. So all the values will be in the form of sine value of 0, sine value of 1, sine value of 2. So this is the first data preparation. And what are the data you are taking? First, you have to prepare the complete data. Then you have to select the radial basis functions. So let's pick the input data as a center. So I'm taking all this input data as centers with the standard deviation psi of 1. Now compute the output of each RBF. So we are directly substituting in the expression given here. So if I take x equal to 2.5. So for each one, I have to substitute these values. 1 second. So 0, 1, 2, sine of 0, all these things I have to substitute here. So if I'm taking x equal to 2.5, exponent of x minus 2.5. What is the first value here? Sine 0 is 0. So I'll substitute here 0 whole square minus 2 psi square. Already I took this one as 1. So this will be the exponential values of this one. So like that, I'll calculate for 0, 1, 2, 3, 4, 5, 6. So C is my center values. So if you see here, C is the centers of the radial basis function. So I'm calculating these values. Now I got each and every value for this particular expression. Compute the output. So this is only for each RBF. Okay. Then final network, we are computing the values from Y values. So Y of 2.5 equal to, I have to calculate I equal to 1 to 7 because here I have 7 values. Okay. So I'm taking all the 0 to 6 means 7 values. So all the 7 values I have to compute. So how I am going to compute? 0.5 into what was 5I of 2.5? It is 0.43. So 0.043 plus 0.5 into second one was 0.326. Like that, I'll substitute all the values. Finally, I'll get y of 2.5, which is equal to 1.25. So after doing this and after doing the total, I'll get 1.25. So my sine of 2.5 is approximately 0.598. We have to adjust the weight in order to reduce the error because sine of 1 second. Yeah. So the sine of 2.5 is around that is 0.14. So this error rate have to be reduced. So in order to reduce the error, so we have to update the weight accordingly in order to get the exact value for this. So by iteratively updating the weights based on the error, we can approximate function more accurately. And this example provides an overview of the RBFN can be used for sin X, and you can explore more examples on this with the different examples. Okay, so this is related to radial basis function networks where we will use the formula for calculating all the networks.